Okay, so we are in the middle of this theorem about uniform convergence and differentiation. It said following that if you have a bunch of differentiable functions, and you knew that their derivatives all converge uniformly, on AB, and the functions themselves, so there existed at some point in AB where the function's values converged. Right, so that this sequence converges, then you could conclude that the Fn converged uniformly to some f on AB. So you converge uniformly on AB, and you could, and the derivative of that limiting function was the limit of the derivatives. Okay, so you could change the order. You could commute limit and differentiation. Okay. Okay. And the first thing that we did was show that last time we showed that the Fn actually converge uniformly. Because if the derivatives converged uniformly, then we can make the difference between them tiny, right? So the difference between, we can make the difference between, Fn prime and Fm prime very small. And then if you have convergence at some point, then the difference between these guys is going to be small. The difference between the function themselves is going to be small over the whole interval, right? And that gave us the Cauchy criterion for uniform convergence. Okay. So anyway, if you don't remember it, go back and look at it. Okay. So so last time we showed that you have uniform convergence to some function, and then part two, we want to show that that actually the derivative of this limit function is the limit of the derivatives. Okay. Okay. So what this boils down to is the following. You say, well, let's consider let phi of t be defined as for each point x, you make these functions phi of t, which is f of t minus f of x over t minus x, and you make these other functions for each of the sequence fn t minus fn x over t minus x. And earlier, we had this theorem, so recall, if we can show that the phi sub n converge uniformly to phi, then from the previous theorem, we get that the limit of phi of t as t approaches x is the limit as n goes to infinity of the limit as t goes to x of phi nt. remember this is the theorem that implies that if you have uniform convergence of continuous functions, then the limit is a continuous function, right? This was the thing that's stronger than that, and so what we just apply it to this case, and you see what happens, right? This thing, as we let t go to x, this gives us f prime, right? And we let t go to x here, that gives us fn prime at x, and we'll let n go to infinity, so that it gives us exactly the thing that we're looking for. Okay. So the only thing we have to do is show that the phi sub n's converge to phi uniformly. Okay. Okay. Right. We already know that they converge pointwise, right? Because each of the f sub n's, the f sub n's go to f pointwise, right? And okay, so right. So again, we'll use the Cauchy criterion. So claiming that these guys converge uniformly. So again, we'll use the Cauchy criterion. So consider, so fix epsilon, and let's consider the difference between Pn and Pm. Okay. Right. We want to find some capital N past which this difference is smaller than epsilon. Right. That will show uniform convergence. Okay. So, well, by definition, this is just fnt minus fnx minus fmt plus fnx, everything over t minus x. Okay, that's just the definition. Okay. But we can control the size of this using the mean value theorem. By the mean value theorem, this equals fn minus fm prime at some c for c between t and x. But we know that that the fn prime converge uniformly, right? The fn prime converge uniformly, so we can make, by the Cauchy criterion, we can make this smaller than epsilon on all of AB, right? Right. So since fn prime converges uniformly, there exists an n such that past that n, fn prime alpha minus fm prime alpha is smaller than epsilon for all alpha in AB. Right? So no matter what C you've gotten, this thing is going to be, this size is going to be smaller than epsilon. So use that n. Right? And then this thing's smaller than epsilon, and that's it. Okay, so it's pretty straightforward. Use that epsilon, then me call this thing star. Use that n to make fn minus fn prime c smaller than epsilon. Okay, so that's the end. Right, because c is just some point in AB. Okay, any questions? Yeah, Luna.
Can you explain the stuff that you used in the value theorem?
Yeah. So I mean, this thing here is just, you know, you're taking this. What is this thing here? It's fn minus fm t minus fn minus fm x over t minus x. Right? If you rewrite it, right? Well, that's a differentiable function, and so just look. The mean value theorem says that for some point between t and x, there's a point where where the derivative of the function attains that average slope. Right? So it's exactly the mean value theorem. Okay, is everyone all right? Okay. Alex, you've got this grimace on?
I don't know.
What?
It's kind of, doesn't that, since it's uniform continuous, isn't you supposed to show it's less than epsilon for all points? But then you just kind of use for point C.
What we're showing is that for any t, we're showing that given an epsilon, there is an n, so that whenever you're past that n, this thing is smaller than epsilon for whatever t you choose. Okay.
Right,
So
okay.
whatever t you choose.
Oh, I see.
Okay. That's what we're showing. Yeah, Sam.
So does that work just because C is an arbitrary point between T and X?
It works because
Right, so C changes for every different T.
C changes for every t, but
Okay.
you know that we have uniform convergence of the derivative, right? We have uniform convergence of the derivative, so this thing is smaller than epsilon, whatever alpha you choose, right? Right, for all alpha, including that particular c.
Right.
Okay. Okay. Anybody else have questions? I was reading some evaluations of a course, like I taught 101 a few years ago, and I think I never looked at the evaluations, but over the break I looked at the evaluations, and one student didn't like the course, said the professor could not carry the material. Took a dry course and made it even drier. So anyway, I hope I'm doing better in this course, but I don't know. I don't know. I think this is cool material, but perhaps I'm not able to convey that how cool it is. It's cool. Okay. So so that's basically the last of our sort of preliminary results about what's so good about uniform convergence. Okay, so like why uniform convergence is so much better than pointwise convergence. So at this point in the text, Rudin throws in something for fun, I think. So a bit fun. Although given my last evaluations, I don't know how you'll take this. It's a continuous nowhere-differentiable function. Okay. This is something that horrified the analysts of the 19th century. When I think it's Weierstrass who came up with this. So they, for a long time, people thought that if you're continuous, then you're differentiable. But Weierstrass came up with this thing that it's continuous, but at no point is it differentiable. Okay. So I'd say if you don't like this, then I have no hope for you. Okay, so I think this is pretty cool. So here's the construction. So okay, let's start off with the absolute value function. Okay. But let's restrain it to the domain between -1 and 1. So 1, the absolute value function like this. And then you extend it to a periodic function. So extend to a periodic function. So you just keep on repeating it. So that is, you define, it'll have a period of 2, right? Every point you just go 2 back until you find, keep on going 2 back until you get back into your original domain. Okay, so you start off with that guy. At this point, we make an observation. We say, well, it's easy to see that the difference is going to be smaller than, the difference between the outputs is smaller than the difference in the inputs. Okay, so that's an easy exercise. It's basically, the thing is slope 1 here, right? Slope -1 here, and then you just need to worry about what happens in between here and here, right? But it's an easy exercise. So just leave it as an exercise. Okay, so this means that that the function has a certain type of continuity. This kind of continuity is called Lipschitz continuous. And on one of your exams, I think you proved that this is stronger than uniform continuity. Okay. So now we make the function. Okay. So that's not the function, of course, right? That function, is not differentiable at these points, but it's differentiable at a lot of points. So we define f of x to be this infinite sum from n equals 0 to infinity of 3/4 n phi for nx. Okay? Okay. Anybody want to say something smart about this? Okay, so you're taking your function and you add on, you speed things up 4 times, right? So it's going to look like this, I think. Right, the first thing that you add on is something like this, right? And it just keeps on going, right? You sped it up. You sped it up 4 times, right? And then you speed that guy up 4 times, and you add it on. Speed that guy up 4 times, and you add it on. Speed that guy up 4 times, and you add it on, right? And each time you multiply by 3/4 to the nth power. Okay, so you take that guy and you scale it by 3/4. You take the next guy and you speed it up, but you scale it by 3/4 of the previous guy, and so on and so forth. Right? And so you see what you're doing. You're basically creating a fractal structure, right? It's sort of like the Coke snowflake, right? sort of like the Coke snowflake that you're doing here. But so anyway, so
you make it shorter. though.
you make it
That's what
shorter.
it's
Yeah.
doing.
So yeah, you take this thing, speed it up, and then shorten it. You multiply by 3/4, and then the same thing. Speed that guy up by this exactly the same ratio, and then multiply it by the same ratio. Okay, so you're adding on spikes. You're adding on spikes everywhere, basically. You add on a certain number of spikes. You add on more spikes, et cetera. It's like the Coke snowflake. Because, you know, you may have seen that thing. You start off with something like this, and then you add on. You take every piece, and then add on corners, and then iterate that. Right? Okay. Okay. So now all these guys, right, are smaller than all the values here are smaller than 1, right, in magnitude, right, and this sum is a geometric series, so this converges. Okay. So by the Weierstrass M test. This means that we have uniform convergence. This series converges uniformly. Okay. And each of these is a continuous function. So you've got a uniformly convergent series of continuous functions, and so you get that the function is continuous. Okay. Okay, so now we're going to show that the function is nowhere differentiable. That is nowhere differentiable. So here we go. Pick any x in R. So just thinking of, how my dry professors back in college tried to, be entertaining. At my first exam, so, I'd taken this course with Andrew Wiles. And Andrew Wiles is from England. He's, a very proper guy. He came in and he would just, put definitions down and go on from there. And it was a very sort of dry course, but it was fascinating, of course. However, at the exam, which was a infinite time exam, we came in at 7 p.m. and we're allowed to stay as long as we wanted. He came in and he said, "Here is your exam. So put on your thinking caps and go!" And his eyes opened wide. And I think that was the most expression we'd seen in him the entire semester. So I at least was sort of like, Professor Wiles. Yeah, that's sort of how I feel like when I'm presenting this to you. Okay, we're going to show that this function is nowhere differentiable. Okay, so pick any x, and then for each number m, so for each natural number m, define delta m for each x. Okay, so for each x, this is going to be dependent on the x we've chosen. Delta m is going to be either plus or minus 1/2 times 4 to the negative m. Okay, and this plus or minus is chosen so that no integer lies between 4 to the m times x and 4 to the m times x plus delta m. Okay, right, this 4 to the m times delta m 4 to the m times delta m is of magnitude 1/2. Okay, so you look at this point, 4 to the mx, and you look at the half intervals, right, to the right and to the left, and you see which one does not contain an integer, right? And then you, if that's on the right side, you make it plus. If it's on the left side, you make it minus. Okay, make sense? You're choosing it so that this interval doesn't contain any integers, right? Right, because the width is 1/2, right? So either this one contains no integers or that one contains no integers.
Why do you need the 4? 4 to the negative m?
You'll see. You'll see. Because we want to get points that are closer and closer to x. Okay. We want to get points that are closer and closer to x to show that we can't differentiate. You'll see what happens. Okay. So now, we want to show that this thing is nowhere differentiable. So consider f of x plus delta m minus f of x over delta m. Okay. Now what's going to happen is we're going to show that this thing is big. Okay. So we'll see. We'll see this actually equals, we can calculate it. It is bigger than something something on the order of 3 to the n. Okay, and that'll be trouble, right? Because for the function to be differentiable, you don't want this thing to be exploding. But as you see, as these delta m's are getting closer and getting smaller and smaller, but this slope is becoming infinitely large, right? And so the function cannot be differentiable, right? But what we're going to see is that if we look at the slope from here to here, the slope is bigger than 3 to the m, basically. Okay. And so if we take larger and larger m's, then we're getting closer and closer, right? And the slopes are getting higher and higher, right? And the reason for that, of course, is because we're adding on spikes that are steeper and steeper. Okay. So let's just see how that works out. It's just a calculation. So by definition, this thing is using this thing here. This is just going to be the sum from n equals 0 to infinity of 3/4 to the n times phi 4 to the n x plus delta m minus phi of 4nx, right? And then everything divided by delta. This thing in the box here, call this gamma sub n. Okay, so we're taking the sum. What we're looking at here is the sum of 3/4 to the n gamma sub n as n goes from 0 to infinity. Is everyone okay so far? We haven't done anything, just put on some notation.
What happened to the 4 to the m, delta m, to the right of the box?
This thing?
Yeah.
What do you mean?
What is that equals? Okay, I guess I'm confused. Is that like down below in the parentheses?
Yeah.
What is that referring to?
I'm sorry.
Is that the entire?
So that thing in the gamma n is the thing in the box. Okay. So I'm just saying that this whole thing here is summation b force b n gamma sub n. Right. Okay. That I probably didn't need to say that. Gamma sub n is the thing in the box. Okay. Okay. So everyone all right so far? Okay. So now, okay. So now notice if n is bigger than m, then 4 to the n times gamma m is an even integer. Right? 4 to the n delta sub m. Remember, delta is 4 to the negative m times plus or minus a half. Right? So you get some power of 4. You get some power of 4 times a half. Right? So it's going to be some positive power of 4 times a half. Right? So it's going to be an even integer. Right? Okay. And so what you get then is phi at some point plus an even integer minus phi at that point. But phi was periodic of period 2, so it's 0. Right? So then gamma sub n is 0. Right? Because phi was periodic. Second thing to notice is that if n is less than m, then by the Lipschitz quality of phi, you know that phi of 4n x plus delta m minus phi 4n 4 to the n times x is smaller than the difference, the size of the difference. Well, the size of the difference is 4 to the n times delta sub n. By the Lipschitz continuity. Right. The difference in the values is smaller than the difference between the difference between the inputs. Well, the difference between the inputs is just this product here, 4 to the n times gamma sub n, delta sub n. Okay. So what does that tell you? That tells you that in that case, gamma sub n in magnitude is smaller than 4 to the n. Right? Because gamma sub n was this thing divided by delta m. Right? So you divide by delta m and you just get 4 to the n. Okay. Now the last one. If n equals m, in that case, what you have is phi of 4m plus or minus a half minus phi of 4m times x. You get this, where there is no integer between this number and this number, right? There's no integer between this number and this number, right? That's how we chose the delta sub m. Okay, but if there's no integer, then the slope of your line is either positive 1 or negative 1, right? Then you're looking at 2 points. You're looking at 2 points, the slope between which the slope is either positive 1 or negative 1. Okay. So in that case, this is just going to be this difference is just going to be a half. Right? Because you're moving, the difference in your input is a half, and your slope is either plus 1 or minus 1. So the magnitude of the difference is either going to be plus a half or minus a half. Right? You're either in a world like this, right? And you're looking at 2 points that are, 4mx and 4mx plus a half, right? You're either looking at something like this, or you're looking at points that are, somewhere like this. Okay. So, right. This is the same thing as that. So the difference is going to be a half. Okay.
The difference is going to be a half, like on the vertical. Is that what you're saying?
For this top part here.
Yeah. So the 1/2. Where does that geometrically? What is that?
That's this height here.
That's the vertical. Okay.
Yeah. That's this height here. Right. Here's our function. Right. Here's our function phi. We know that there's no integer between this number and that number, right? And so the slope is either positive 1 or negative 1, right? So the difference is going to be a half. Okay. So then, what does that give us? That gives us that gamma sub m is going to be, the magnitude of gamma sub m is going to be the absolute value of a half divided by the absolute value of delta sub m, right? But the absolute value of delta sub m is 1/2 times 4 to the negative m, right? So in that one case, we know we're going to get 4 to the m, right? We have something divided by 4 to the negative m. In other words, 4 to the m. Okay.
Do you need 4n?
For n?
To the n. Because
It's the same. N and m are the same, right? In this case, same thing. N. So in that case, we get 4 to the m or n, whichever one you like. Okay. Okay. So now let's look at this slope and see what we get, what we can say about it. Okay. So this thing here, right? This thing, which was 3/4 and gamma n. We know we can truncate it, right, at m, right? Because past the mth term, all the gammas were 0. Okay, so we get a finite sum, right? We get a finite sum, and let me break it into 2 parts. The top term
Can you
before-
remind us why past m all the gammas are 0? Is that what we just did?
That's what we did right here. The first thing we showed, that
Okay.
if n is bigger than m, then these things differ by an even integer, and so it's
Zero.
going to be 0. So we have the top term, right? For that top term, we knew that gamma sub m really was just 4 to the m, right? By this thing here, right? And then we have all these other terms. Sorry, we're looking at the absolute value of this. Right? Well, no. Is it all right? You look like you have a question. No, you don't. Okay. So, okay. So, and we know that all of the gamma sub m's are smaller than 4 to the n. Okay. Now, what I'm going to do is I'm going to, I have this 3 to the m from this first term, and I'm going to say that this sum is bigger than 3 to the m minus the biggest thing I could get here by substituting in 4 to the n for all the gamma sub n's. Okay, so I'm going to subtract off the biggest thing I could get here. Okay, that turns out to be positive, so I'm justified in taking off my absolute values. Okay, so I just make this thing as big as possible, and I subtract it off. That thing is actually smaller than this, so what I'm doing is actually legal. Okay. So then, what you have here is, of course, just a geometric series. Well, part of a geometric series, right? 3 to the n from n equals 0 to n minus 1, right? If you remember your calculus, this turns out to be 1 minus 3 to the m over 1 minus 3. So the partial sum for a geometric series, even if it doesn't converge, right? Even if the series doesn't converge, the partial sum you can get a value for, right? So I get this, and that works out to be 1/2 3 to the m plus 1. So what does that tell you? That tells you that you have, for every x, you have these delta sub m's, right? Delta 1, delta 2, delta 2, delta 3, that get arbitrarily close to x, and for which the slope of the secant line becomes arbitrarily large. In other words, the function cannot be differentiable at x, and x was arbitrary. So it's not differentiable anywhere. So this was something that really horrified the analysts of the 19th century, and made them reconsider what a function was. Yeah, and I think this is really what led to like all these epsilon delta arguments of wire stress. Like redefining the limit in terms of epsilons and deltas instead of in terms of infinitesimals. Yeah, Jenna.
I forgot what I said.
That's the point of my interruption. Yeah, Mia.
Wait, why would this lead to them reconsidering everything in terms of epsilon delta? Because they doubted whether their infinitesimal arguments were still rigorous because of this?
I think so, yeah.
Okay.
Yeah, that they had been going by using a certain intuition, right? And that intuition, I think, really was that functions were continuous. That anything that was a function could be, that everything was differentiable, actually. Okay. So that every function was differentiable. But then if you think of a function as just something that takes in a value and spits out a value, then you see that you can have a function that's continuous and nowhere differentiable, which is awful. And so they had to redo everything. Yeah. So.
Is it possible to actually kind of picture what this function looks like? Besides just like the. Like
well, I mean, it's going to look. It's going to be something like so the Koch snowflake is where you're adding on positive things. Well, it's not even a function here, but you're always adding on things in one direction. Okay, and you keep on going with like that. So for every interval, you chop it in thirds, and then you add on. You mess with the middle third of it by adding on like this bump here. Right. Okay. And then you take every straight line segment, and you do that. You keep on doing that. You take every segment, you chop the middle third out, and then you add in this thing here. Okay. So that's almost what we're doing here, except what we're doing is we're adding on in both directions. We're adding on something that goes like this. Okay, so we're adding on a spike in this direction and a reverse spike in the other. Well, no, actually, I'm sorry. No, we are adding on positive things. It's just a bigger spike here and a smaller spike here. Okay, so right, and then you just iterate that. So you take your absolute value function, and then you add on this thing to it, multiplied by scaled to 3/4 the original height, right? And so you'll have this function, and it will go up here. It'll have like do something like this, and then over here, no, not sure, something like this. I'm not sure exactly, but you keep on doing that. And you're basically adding on spikes to it at every time. And then it will become more and more jagged. Yes, Sam?
Is the 3/4 scaling just necessary so at the end there it's easier to write out the...
Otherwise it will diverge to infinity.
Okay. Oh, okay.
Yeah, right. It won't converge. Okay. Okay, so... Okay, so that's that. Okay, so we're basically heading into the final stretch of the course, and that last bit has to do with something that's like a generalization of the Bolzano-Weierstrass theorem. So I don't think we gave it a name earlier, but the theorem that in our every bounded sequence has a convergent subsequence. So that thing is called the Bolzano-Weierstrass theorem. And so what we would like is something along those lines for sequences of functions. Right? What kind of conditions do we need to guarantee if you have a bunch of functions, what kind of conditions do you need to put on them to guarantee a convergent subsequence of functions? Okay, like what is the analog? What this boils down to is compactness, right? You've got a bounded sequence in Rn, so it's living inside a closed and bounded set, right? That's compact. That allows us to get the convergent subsequence. Okay, so you're sort of wondering, what is compactness for the space of functions? right, with respect to uniform convergence, right? What kind of compactness will guarantee uniform convergence? Okay, and so our near-term goal, and maybe our final goal, I'm not sure, is the theorem of Ascoli-Arzelà, which answers that. Okay. So that's the big idea, and let's head towards it. Okay. So the boundedness of sequences of functions. Like, what do we mean, by a bounded sequence of functions? Right? We had, in Bolzano wire stress, we need a bounded sequence. Well, what does that mean for our functions? Bounded in what sense? So we'll have two notions. So you have a sequence of functions. And these are complex value functions. You have a sequence of complex value functions on a set B. If for each x and e, the sequence fnx from n equals 1 to infinity is a bounded sequence, then we say Fn is pointwise bounded. Okay, so for each you take each point and you look at the values at that one point. And if at each point the function that collection of values is bounded, then you say that the sequence of functions is pointwise bounded. Okay. Now that's different from the stronger second condition. So let me say it this way. Sorry. Remark. Equivalently, there exists some function phi from E to R such that fnx is smaller than phi of x. For n equals 1, 2, 3, etc. Okay, so there's some phi of x, and at each x, all your values stay lower than that phi of x. Okay. Now that phi of x could be increasing, right? But we don't care. All we care is that at each point, the values are all bounded, right? We're pointwise bounded.
Can they be bounded by infinity? Is that considered bounded in this case?
No,
or
no. So phi, this guy is a real value function,
okay.
not an extended real value function. Okay. So second definition: if there exists an M such that fnx is less than M for all x and e, for n equals 1, 2, 3, etc., then we say the Fn are uniformly bounded. On E. Okay. So this is different. This is saying that there is a constant, right? There's a constant M, and at every point and for every function, your values stay bounded by those uniform values. Okay, so there's a uniform bound for all the values, for all the inputs and for all the functions. Okay, here the bound depends on the point. Here the bound is independent of the point. Okay. And Ryuden gives an example to answer the following question. Suppose you know that these guys are uniformly bounded. Suppose they're uniformly bounded and they're continuous on a compact set. Does that imply that there exists a pointwise convergent subsequence? And the answer is no. So even if you're continuous on a compact set and your functions are uniformly bounded, still you have no guarantee of even a pointwise convergent subsequence. Okay. And the example uses some stuff that you haven't seen yet. He refers to chapter 11 in this chapter. So I don't. Let me sort of sketch out the example. So says, well, look at these functions. Let f sub n x be sine of n times x on 0 to pi. If there exists some f and k that is pointwise convergent, then you would know that the limit as k goes to infinity of sine nkx minus sine nk plus 1 x is 0. For each x, you take k going to infinity, then this would be 0. That's what pointwise convergence means. But that would imply that the limit of the same thing squared is 0. Okay, and then he pulls out something which we can't prove yet. Says that would imply that there's something called the dominated convergence theorem. So Lebesgue dominated convergence theorem. That says that under certain conditions, then the integral of the limit is the same thing as the limit of the integrals. You can change limit and integration. Okay. It applies in this case, so what you would get is that the limit as k goes to infinity of the integral from 0 to 2 pi of the square is 0. So you can change Lebesgue dominated convergence, tells you can change integration and limit. You integrate 0, you get 0. So that's the limit of the integrals must also be 0. But that's a contradiction, because if you work out this integral, it turns out to be a constant. It turns out to be, it's actually equal to 2 pi. So it's a calculus exercise to see that this actually equals 2 pi. Okay, so you get a contradiction. So even though you've got uniformly bounded functions, right? They're all continuous, they're all in a compact set. There's no pointwise convergent subsequence. So what we're going to do, and I think we're going to have to put it off till next time, is to show some conditions. We'll show sort of a weak theorem that tells you when you do have a pointwise convergence subsequence, and then we will try to go for, well, hopefully we'll try to get to Ascoli Arzela next time.